Hey guys, so I'm someone that loves to play retro games. I emulate games on my laptop and I play stuff like Mario or Sonic or Pokemon. But the thing is, playing those old games with these controllers it doesn't hit the spot. So I wanted to make my own retro controller. So I was thinking about how to go about this. Then I realized when I was younger, I used to have these Famicom clones. So these things, they're pretty much the same as the Famicom, which is like the Japanese release of Nintendo, the NES. But they're an SoC, they're a system on a chip. And they came with controllers that look like this. And this looked pretty perfect to me. Like it gives the same vibes as a retro game controller, so I can play games with this. But the thing is, these proprietary ports, they don't exactly speak to my computer. I needed a player to translate the inputs from these controllers to my laptop in a way the laptop can understand. So the thing about these old controllers, right, is that for a lot of them, they're pretty much just buttons on a wire. So a controller like this is functionally no different from this. And that means that every time the controller wants to send an input, it just does this. But then Nintendo took a different approach with their controllers. They used something called a shift register, and that works a bit like this. So the controller just takes all the buttons and stores it in a register, and the CPU just pulls from the register when it needs it. So the controller goes to the CPU. But the advantage with the polling, which is what this is called, is that you can press multiple keys and it would just go in at the same time. The CPU can read multiple keys at a time. So if you wanted to move diagonally, for example, you can just press top and one of the side buttons and it would be diagonal. It would be top and side instead of top side, top side, top side. But the thing is, to translate these inputs, it just adds a whole new layer of complexity because now I have to use a clock signal to get the bits out of the controller. So I have the controller wired up to my Arduino here, and the way it works is pretty basic. So the controller has three wires coming out of it. Apart from the power wires, the 5 volts and ground, there's 3 wires. One's called latch, one's called clock, and one's called the data. So I have a bit of a demo setup here so you can understand the shift register better. So this little chip is a shift register, and this button is the latch or the strobe as you saw in the pin diagram. And this is our clock, which is just a pulsing wave. And this represents our controller input. So 1 could be A, 2 could be B, and so on. So right now I have 1 and 2 selected as high, so it just means that 1 and 2 are pressed. But then if I press these buttons, it has no changes in the D2 output. That's because right now the latch is off, so there's no input captured in the chip. But the second I press the latch, you can see that the number of samples jumps up and the D2 light blinks every once in a while. So that means that the signal that the chip is captured is pushed out through the output serially. So whatever's in here is reflected inside the chip, and that's just being pushed out one after the other. So once we're done here, once you click stop, it'll make a .bcd file, which is just a waveform, and I'll show you what it looks like. So I have GTK wave opened up here, which is just a waveform analyzer, and I just have to select our logic file from this, and I just add all of our signals. And right now we can't see anything because it's in a very zoomed in time frame. So I can just zoom it out and you'll start seeing the signals, and yeah, there it is. So here we can see that this is when we pulsed our latch, and the moment the latch pulsed, the shift register started outputting the values from the values inside the register. So at this clock pulse it's a 1, and at the next clock pulse it's still a 1, and then it's 4 zeros. As you can see, there's a 0, 0, 0, and a 0, and then there's 2 other ones, which is exactly what our switches are. So it's a 1 1, a 0, 4 zeros, and then 2 1s. So that's basically how a shift register works. So to demonstrate that, I have this code set up over here. It's what it basically does is it pulls the latch high and then low, and then it pulses the clock 8 times, and it shows you it prints out what the value is. So if I press A here, the wire is a bit screwed here. So if I press A here, it shows A, and if I press B, it shows B. And because of Nintendo's smart engineering, if I press both together, it shows both the buttons. So I can press start, and if I press upright, it can use upright as diagonal instead of just upright, upright, upright as normal controllers would see. So yeah, that's pretty much all we need to know to translate this to our computer.
One eternity later.
So I'm just about done setting everything up. So I've basically made the Arduino code just send the raw bytes to the laptop, and I have this code on the laptop which takes those bytes and uses a Python library called vGamepad to convert these button presses into an Xbox 360 button press. So to be fair, we're still using the same Xbox 360 gamepad that would have been using, but it feels more real now. So I'll just use it to play Mario. Just open RetroArch. I just open the recent one, right? I'll load the Famicom code, and I'll open Mario, which I acquired very normally, legally. So I can just oh yeah, shit, I forgot to run the code. Right, so I have the controller connected now. I can just play Mario. The sound is not working. Yes. So it works pretty darn perfectly. Don't judge me. Don't judge my shitty ass gameplay. I've played this so many times I've gotten no better at it, as you can see. Alright, so that's pretty much it for this video, and if you like the content, please like and subscribe, and I will leave the codes in the description below for any of you that might have one of these old ass controllers lying around. I will also leave all the resources, the pinouts and stuff I find in the description. So thanks for watching. Bye bye.